This video is an introduction to operational amplifiers, or op-amps. One of the most versatile of all electronic devices is an operational amplifier. An op-amp is a semiconductor integrated circuit composed of many, possibly dozens of transistors that can be employed in many different ways to manipulate an analog that is a continuously varying signal. With the exception of design engineers in big manufacturing companies that make circuit chips, no one thinks about the arrangement of transistors inside an op-amp. Instead, we assume that the device follows a few simple operating rules, and then we design circuits around these properties. An op-amp has a single output and two inputs. One marked with a negative sign inverts the sign of a signal if it is applied there. The other is marked with a plus sign and is called the non-inverting input. There are basically two rules that govern the behavior of an ideal op-amp. The first rule says no current flows into the op-amp at the inputs. The second rule says that using feedback, the op-amp drives the output until the voltage at the inputs match. So let's take a look at how an op-amp might work in a few circuits. So here's the first configuration we're going to look at. I'm using this circle here to represent our signal source. And I've indicated here that it produces a voltage. So we're putting that voltage at the input here. So we're going to have V in, we're calling it, at this particular input. Now, the first rule for an ideal operational amplifier says that we won't draw current at the inputs of our op-amp. So that means that we're not going to draw current from our signal source. We're not going to distort it. That's a good thing. The second rule says that if there's a feedback loop, the op-amp will try to drive the voltages at the inputs until they match. So this voltage is going to match the input at the V plus side, and so that's going to be V in there. And since it's connected by a very low resistance path, the output signal is just going to equal the V in. That seems like a silly thing to do. What good have we done here? What have we accomplished? Well, we've gained two things. First of all, this has a very high input impedance. That means it's not going to draw current, so there's no distortion of our signal. The second thing is that, although I haven't shown it here, this op-amp is powered by separate power supplies. So if devices downstream have low input impedance, they can draw current, and this is not going to change the signal. This is a very frequently used circuit, and so we give it a name, voltage follower. It's often used in different instruments that are used to measure a voltage signal from some transducer or detector, and this is very useful for buffering, essentially, the signal source from devices downstream from this point where we might be manipulating the signal. We often have a device that produces a current signal. Voltages are easier to manipulate than currents, so we are interested maybe in converting this to a voltage signal. Here's a common method for converting current to voltage. So here we have a signal, and I'm going to call it I in. So I in comes into this point that's connected to the inverting input of our op-amp. Now, we think about this junction, we think, well, maybe current goes in here, but our first rule for an operational amplifier says no current's allowed into the inputs of the op-amp. That means all the current has to go back through what we call the feedback loop. So the current in the feedback loop is equal to the current that comes in from our signal source. So let's call this resistance RF for the feedback resistance. We know that there's a current through this resistor, so there has to be a voltage drop, and that's given by Ohm's law, equal to I in times RF. If we notice that the current's going from left to right through this resistor, then the voltage over here has to be downhill from the voltage over here. The voltage at this point we're going to call V minus for V at the inverting input. This is the output voltage, so V out is equal to V minus downhill or minus from I times RF, just the voltage drop through the resistor. Well, what's the voltage at this point? Well, that's the input voltage, and we have a feedback loop. So the operational amplifier is going to drive the input voltages until they match. In other words, V at the inverting input has to be equal to V at the non-inverting input. So this is the non-inverting input, and look, we've attached that to ground. That's 0 volts. So V minus is 0, and then minus IN times RF. If we tidy this up, we have our relationship V out is minus IN times RF. So we have an output voltage that's proportional to the input current. The sign changes, but we see that the proportionality constant is just the feedback resistor. We can think of this as a gain factor, so that if we need more signal, we need a larger voltage for a given current, we just use a larger size resistor. This is such a commonly used technique that this configuration is known as a current follower or a current to voltage converter. Let's analyze this circuit. Let's start by making some simple observations of current and voltage wherever we can. Now, most obvious thing to do is to see this ground and say, oh, okay, the voltage at that point has to be 0 volts. Well, that's equal to the voltage at the non-inverting input, so V plus is 0. Now, we see that there's a feedback loop, so the op-amp is going to try to drive the inputs to match in voltage. So this one has to match this one, so the non-inverting input's already set, so this voltage has to be 0 as well. We have a voltage input as our signal. Let's imagine a concrete example for a voltage just to help think this through, what the implications are of that. Let's suppose that we had plus 1 volt at this point. What would that mean? 1 volt here, 0 volts here. There has to be a current going through here in this direction. So let's call this I in. We think about that. The current's going to come to this junction, and we think, can it go into this input? No, that would violate the first law for our operational amplifier. So all that current has to go through the feedback loop. So this feedback current has to be equal to the input current. Now we see that there's a current through here. There's a voltage drop in the feedback resistor, and that is going to be equal to the current coming in times the feedback resistance. It goes from left to right here, so the voltage over here at the output has to be downhill from the voltage here. So V out is equal to V at the inverting input minus the voltage drop in the feedback loop, which is just I in times RF. And now we know that the voltage at the inverting input is 0, so this is minus I in RF. Our signal is not just a current, it's a voltage. The relationship between the input voltage and the input current is just the voltage drop across our input resistor, I in times R in. So if we solve for the current in that resistor, it's Vn over Rn. So substituting up here, we get, I'm just going to rewrite that to point out a couple of things. We have minus Vn times the ratio of Rf over Rn, so that we see that our output voltage is proportional to the input voltage. There is a sign change. And then the gain factor is the ratio of our resistances, the feedback over the input. Some people call this an inverter amplifier. I prefer to call it a simple gain amplifier. Here is a photo of some commercially available operational amplifiers. They often have 8 different connecting pins or leads. The longer device with more leads actually houses 4 separate op amps in a single package. In our discussion so far, we've omitted showing connections between the operational amplifier and the power supply for simplicity. Most op amps need to be connected to both a positive and a negative supply voltage of equal magnitude. This can be as simple as 2 radio batteries that provide a plus and a minus 9 volts, or other power supplies that are both plus or minus 12 or plus or minus 15 volts. The magnitude of the op amp's output can never be greater than the magnitude of the supply voltage. In fact, the maximum output is typically limited to roughly 1 volt less than the positive supply and about 1 volt greater than the negative power supply.